Greetings. My name is Gabriel Aviles Cordero, and I will be talking about my subsystem, which is composed of mechanical actuators, limits, and control systems. The presentation will consist of the following divisions: a subsystem trace study, subsystem architectural components, subsystem risk assessments, and finally a project planning. For our subsystem trace study, we took the responsibility to define three different options to efficiently evaluate the best development mechanism. Our first concept is a closed-loop system model with a knee pulley and ankle slider and sensors with two inputs and two outputs. The subsystem is composed of an initial input given by a command joystick. This is another subsystem by another of my companions. The input is received by a processor, in our case an Arduino, connected to a DC motor driver. The motor driver will be directly connected to a power supply. After the input is processed, it will be read by the actuators, which will produce an output. That output is a displacement of the actuators. This output fits the feedback system composed by the subsystem sensors, which will be used to feed the processor additional information together with the control inputs. Additionally, we have a second input point provided by a manual emergency button. The purpose of the button is to provide immediate cessation of device activities to maintain patient safety and protection. Within the subsystem, we define a list of specifications and features, among which we have the operational voltage it is defined as between 13 and 26 volts. The frequency that is in the interval of 50 to 60 Hz. Operational weight between 5 to 7 pounds. Emergency systems. There is an emergency system. There is a limiter systems. The investment cost is $270 to $350. The system is composed of 9 major components and have an operational temperature of 30 to 40 degrees Celsius. Our second concept is an open loop system, knee pulley and ankle crank sliders. This consists of an open loop, so when receiving the input from the joystick, our output will be the same movement of the device, but without producing any feedback to allow us to update the incoming information. This implies that the system will have no sensors and no emergency system. As in our first model, we define the same specifications, which are as follows: the operational voltage between 9 to 15 volts, the frequencies between 50 to 60 Hz, the operational weight between 2 to 4 pounds. It doesn't have an emergency system, it doesn't have limiter systems. The investment cost is between $200 to $250, and it has a component of a number of 5 major components. The operational temperature is between 30 to 40. Our third and last concept is the continuous closed loop system with actuators. It is the most similar model of the first one mentioned, since it consists of a closed loop, but unlike the first one, this last one does not use a feedback system by means of sensors. In theory, The model, upon receiving an input, will continue to perform the function continuously until it is dictated otherwise without updating its output. As in our two previous concepts, we define the same specification criteria, which are an operational voltage between 10 to 15 volts, frequency between 50 to 60 Hz, operational weight between 2 to 4 pounds. It doesn't have an emergency system. It doesn't have a system limiters. Uh, it have uh, it have an investment cost of $200 to $250. It have five major components, and the temperature, operational temperature, is between 25 to 30 degrees Celsius. Once the three concepts were defined, we carry out a decision matrix tool using our specifications to select the most favorable and efficient concept. Each of the criteria was given a weight that defined its importance. As you can see in the result of the matrix, the subsystem that best suits us is the first concept mentioned, with a score of 255 compared to a 202 for the second concept and 216 for the third concept. Once selected our concept, we proceed to decompose the architecture of our subsystem in its components, which are inputs, actuators, sensors, and outputs. In our inputs, we have the joystick controllers and Arduino board receiver. In our actuators, we have our ankle actuators and all our knees actuators. Uh, we need two actuators in both systems or joints. We are considering a crank slider mechanism or DC motor with a pulley. We are also considering a pulley mechanism for the knee and a 12 volt DC motor. We also divided our sensors components into ankle sensors and knee sensors. In our knee sensors, we have the options to use line positioning sensors or laser positioning sensors, while in our ankle sensor, we have the option to use laser position sensors or resistance position sensors. Lastly, our last component is the output, which is the movement of caused by actuators, and we also have our second output, which is the output signal feedback. Uh, by breaking down our systems, we make it easier for us to identify the resources available to meet our operational objectives. Now, our device and subsystems are intended to facilitate access to rehabilitation throughout the CPM's machine. We define a CPM device as a medical product intended to provide physical rehabilitation assistance to various patient groups. Our subsystem should be able to support the joints of the lower extremities of the body, with a major emphasis on the knee and ankles. By this means, the product should be able to accommodate patients with a maximum length of 120 centimeters. Additionally, it must provide a load capacity to support a maximum weight of 300 pounds. The range of motion in the joints are knee with a minimum of -5 degrees, a maximum of 110 degrees, ankle with a minimum of -20 degrees and maximum of 50 degrees, hips with a minimum of 0 degrees and a maximum of 115 degrees. We assume we assume optimal humidity and temperature. For this statement, we have the objective of finding or calculate the torque necessary to carry out a movement, and calculate the energy consumption necessary to carry out the work of the actuators, calculate and calibrate the input rate of the sensors, and determine the max load. Using the architecture breakdown mentioned above, we use other decision matrix tools to select the best option of our components. We understand that our main components are the actuator system and the sensor system, so we created two matrices, one for each subsystem. In sensor matrix, we compare the subsystem at two joint points, knees and ankles, and the criteria used for the MOPs defined for a sensor subsystem in addition to those mentioned in the original specification. Our criteria are frequency, accessibility, measurable distance, repeatability, durability in years, maintenance, and cost. The proposed sensors used for the ankle are laser precision sensor and displacement resistance sensor. The sensor proposed for the knees are positioning line sensors and laser precision sensors. The laser precision sensors and the positioning line sensors were defined as the optimal option for the ankle and knee respectively. The same action was taken for the actuators. In this, we adjust our criteria for the corresponding specification whereby we have frequency, weight, torque, precision, durability, maintenance, and cost. The mechanism proposed for the knee were pulley mechanism, translator mechanism. The proposed mechanism for the ankle were the translator mechanism and the pivot-based mechanism or multiple sliders, of which by means of the evaluation the pulley mechanism and the single crank slider were defined as the optimal option for the knee and ankle respectively. As part of the evaluation of the subsystem, we also have to define the possible risks of action to be taken to mitigate them. That is why we created a list where these risks were defined, and a Sophia diagram is used to represent the impact of the risk. Our list is multiple engines may suffer from desynchronization or excessive power consumption. Excessive weight can cause deformation of the motor body. Failure to follow natural range of motion can cause injuries to patients. Excessive price can cause manufacturing shortage. Excessive potency can lead to disproportional power consumption. Excessive load and poor lubrication can cause friction and overload to the motors. Overheating the motor results in the decrease in power, misfiring, burning of components, among others. And lastly, the absence or failure of the emergency button system may cause injury to patients and malfunction of machinery. This is due to the unnatural displacement of the joints. Our mitigation strategies were establish a routine monitoring along with establishing a validation action to prevent desynchronization. Maintaining the weight of motor under the standardized weight range. Calibrate the device with specific range parameters by means of sensors. Research and market studies to acquire the most efficient system. Apply electronic isolation technique to avoid splashing. Design an ongoing user maintenance plan. Develop an efficient heat dissipation system and considering the possibility of insulating material around components. And finally, to provide the stopping system with an intuitive and simple mechanism. Finally, as our last slide, we show you our project planning for the phase C. Thank you for your attention and we hope you enjoy our presentation.